Welcome student to this lesson. We will talk about the line integral of vector field. So I'll start directly with the first example. You will find out in this example we need to find the integral of the function x over y, and there is two new things here. We have c, which is a curve, and there is a ds. We will see what this means in a second. This is, we call it line integral because we are now doing the integral not through a straight line from a to b as before, but through a curve that is parameterized by t. So usually the setup for those kind of questions is that we will give you the parameterization of this curve, or sometimes you have to find the parameterization, and this is what we will see in example number 2. So if we have this equation, what we are going to do is I will remove every x and I will write t cube. I will remove every y in the question and I will write t power 4, and I will make my integral goes from 1 to 2. So if we start solving this question, we will have the integral x over y ds. This will equal to, instead of x in the top, I write t power 3. Instead of y in the bottom, I will write t power 4, and I will make the integral goes from 0 to 2. So this is the first step, is to replace x by its value in t, y by its value in t. Now, there is only one thing that we need to focus, which is ds. ds has a formula which is the same as the formula for finding the distance. So it will be square root of 2 things squared dt. What shall we write here? In the first one, we will write the derivative of x with respect to t. So dx by dt, or just in short, x prime. And here I will write dy by dt, or in short, this is just y prime. So I will go to my function here. I will take the derivative of t power 3 and I will write it here. I'll take the derivative of t power 4 and I will write it here. So I'll get 3t squared, and this will be 3t power 4. T power 3. So this is how we move from the line integral to the usual integral that we have encountered before in calculus 1 and calculus 2. Now this integral, all what we need to do is we just need to solve this integral. So I go from 0 to 2. Now t power 4 and t power 3, they will cancel each other. So I will end up with 1 over t. I will have this square root dt. 3t squared, and if I square it, we will get 9t power 4 plus 16t power 6. Now I will take t power 4 as common factor. So we'll get here square root of t squared, t power 4, 9 plus 16 t squared dt. I'll distribute the square root on both. So I will get square root of t squared, square root of 9 plus 16 t squared dt. Now, of course, square root of t squared, this should equal to the absolute value of t. But my values for t are already in the positive side, which is from 0 to 2. This means the absolute value of t will be exactly equal to t. So we will end up with this integral from 0 to 2, 1 over t times this square root. Now this is after the cancellation with, this is t power 4, sorry, so it will be t squared. After the cancellation, what we will get up is only 1t, and this one I will write it to the power of half. So this would be equal to integral from 0 to 2 t 9 plus 16t squared power 1 over 2 dt. Now, if you look at whatever inside this square root, you will find we have t squared and the derivative of t squared, which is 2t, but at least the t is here. So here we will use the substitution method. So I will directly use the substitution method. You can try it at home by finding the suitable u that you need to use. So here is by substitution, this integral will turn out to be from 0 to 2. This integral will be 9 plus 16t squared power 3 over 2, and then you multiply by t over 3. But because I'm missing the derivative of t squared, so here I will divide by 1 over 32. You are wondering why I choose 32, because remember, if you take the derivative of this one, you multiply 2 by 16, so here must be 32. And because of lack of 32, I need to divide by 32. And now we just go ahead and substitute 1 times 2, 1 times 0, and we will find the final answer. Please pause this video now, go ahead and solve it by yourself, starting from the beginning, from the scratch, by replacing t by x by t cubed, y by t power 4, and use this formula for the ds, and do all the steps without looking at this video, and then play it again and check your answer. Please write for me in the comment what will be the final answer that you will get here. Now, we will go to example number 2. So I advise you now to pause this video. Try to think about it yourself. Try to compare it with example number 1. See what is the difference between example 1 and example 2, and how you will solve example number 2. So please pause the video. Okay, welcome back to this example. I think you have noticed what is the main difference between example number 1 and example number 2. In both, I need to find the line integral with ds and the curve c, except in this one, I don't have the parameterization. So the first step we will do, and this is the first step, we need to find the parameterization of the curve c. I don't have x in terms of t, I don't have y in terms of t, I don't know t from where to where, so I need to find the parameterization by myself. Now, how we would find the parameterization? The only information I have is 2y equal x squared, and I need to parameterize this equation. Now, if you remember this equation, this is just an equation. It is one equation into two variables or two unknowns. And we know if we have one equation into two variables, one of them we will call it t, and that will be the free variable that we are talking about. So I will call x to be t, and then I will find y using this equation. So if I substitute x to be t, I will have to divide by 2 to get y to be t squared over 2. And that's how we find the parameterization for this curve. So this is the parameterization. Of course, the parameterization should be complete after you tell me t between what and what. Now, we have to think about it here because t actually is x. So if we look at this information here, he's telling me that my curve starts at the point x equal to 0, y equal to 0, and it ends up at the point 2 and 2, x equal 2 and y equal 2, which means start from 0, you end up at 2 in terms of x. So my integral will be from 0 to 2, and that will find for me the parameterization. Now, example 2 is just a repetition of example 1 because we have a line integral and we have already parameterization. So what we will do in step number 2, we evaluate the line integral. So how do we evaluate the line integral? Again, we do the same steps here. I have x cubed over y. So what will happen here is we need to evaluate x cubed over y ds, and this is exactly integral from 0 to 2, because the t is from 0 to 2. You remove every x and you write in term of t. Remember, x was only t, so I get t cubed here. But the y was t squared over 2. And then we have this square root dt, where we write the derivative of x squared plus derivative of y squared. Now, what's the derivative of x? Was x equal to t, so derivative of t is 1. Derivative of y is actually t squared over 2. So if you take the derivative, this will be 2t over 2. So I think the answer will be just t. Now, all what we need to do is little of simplification. T cubed with t squared will cancel each other, so I will get only 0, only t. Now, the 2 is down here in the denominator of the denominator, so it will just jump up here, so I will get 2t actually. And then I have the square root of 1 plus t squared dt. And that's, again, substitution method. We have a function which has derivative 2t, and that derivative is already sitting in the integral. So this is the perfect scenario for the substitution method here. So I will just do it 1 over 2, 1 plus t squared. And now you can just try to do it, the integration. Let me do it in green here. So it is from 0 to 2. This would be 3 over 2, 1 plus t squared. And then you will do 2 over 3. Now, all what you need to do is substitute 1 times 0 and 1 time to be 2. So if we substitute 2, this would be 2 over 3. And then we will have 17 to the power of 3 over 2 minus 2 over 3. That should be, sorry, not 17, it should be 5. 3 over 2. And that should be the answer for this question. Thank you for watching. In part 2, we will do the same line integral, but instead of having ds, we'll have to be dx or maybe dy.